There are sound waves and electromagnetic waves around us all the time, every day. When you go to the beach and hear and see the waves rolling in, or even using microwaves to heat up our food. Your FM radio in your car also uses electromagnetic waves. We will be focusing on sinusoidal waves, which have a very particular shape and are produced by a source that oscillates with simple harmonic motion. As you can see in this figure, waves have a wavelength, a velocity, and there's a third component, which is the frequency. This particular image is showing this wave in comparison to a sound wave. A sound wave is a longitudinal wave, which is a push-pull motion, as opposed to a transverse wave, which is up and down. It is often easier and more convenient to think of a sound wave as a pressure wave, which oscillates around the atmospheric pressure. The wavelength is the distance between two crests, or in this case, the points of maximum compression. When this wavelength hits your eardrum, the vibrations it causes allows you to translate it into the sound that you hear. This table shows the range of hearing for different animals. If you look at human, anything below or above 20,000 Hertz would not be audible. Elephants use a very low frequency to be able to hear each other over very far distances, whereas bats use a very high frequency, which is better for things like echolocation. These very high frequency sounds that we cannot hear are called ultrasounds. This equation shows the relationship between all of the components of a wave. The V stands for the velocity, the lambda for the wavelength, and F for the frequency of the wave. This equation works for both electromagnetic as well as sound waves. Looking at the electromagnetic spectrum, we can see that the frequency of AM and FM radio waves is a lot smaller than X-rays, and it increases as you move up the scale. We observe the area labeled visible light every day, and it is actually the only part of the spectrum which humans are able to see. A light wave is an oscillation of the electromagnetic field. All electromagnetic waves will travel with the same speed, which is 3 × 10⁸ meters per second. And although we are able to see all of the visible light portion of the spectrum, the differing wavelengths cause us to perceive them as different colors. So next time you observe things around you, the grass, plants, trees outside, or maybe even take a trip to the beach and observe the waves and listen to them and look at their shape. You can think about the different frequency, wavelength, and velocity of each wave.